So now I'm going to go ahead and go into recursion. So, all right, recursion. Oh, let me minimize that so that we guys aren't all intimidated at first. So I want to make sure I go through it once. So recursion basically allows us to, well, first of all, does anyone know what recursion is? Just thumbs up if you heard recursion before. Okay, so I see a couple people. So if you did computer science, you've probably been exposed to this at some level. Recursion basically is a way to repeat a function or a process over and over again within itself. If you ever know like fractals, for example, you can think of those like recursively generating. But recursion allows us really easily to actually go into something like JSON and XML because we don't know what the structure is. Like with a CSV, we know the structure. We know how many columns there are from the very header, right? If we see the header or even the first line, right, if there's no header, we can see how many columns there are and we know they're separated by commas, right? Or if there's TSVs, tabs, right? But the point is we know the structure right away. With JSON and XML, you have no clue how many like nested elements there can be within a JSON. And each part can actually have its own, like even if you go into one nest and then you go to the next child, that could have a completely different structure from each other. So this is what recursion actually does really well. So recursion basically allows you to repeat the same process over and over again. So the way I kind of think of this is that if you look back on, let's see here. So if you look back on here, is that each part of this, like in a JSON file, right, is basically like, you can see like this JSON, like this is all valid JSON. But then also I could look at just one part of this, and that's also valid JSON. So if you imagine like, well, if this is JSON, we basically can go into that pop-up part and then look at just that part and process it through, or we can go from the very beginning and process it out and going inward. So since they're all kind of like similar to each other, we can basically use recursion to repeat the same process over and over. So that's the motivation of why we're talking about recursion. Just know recursion is generally just like really difficult to get your head around. It's not usually considered like the most easy thing to remember, or I should say understand. So just know that this stuff in general, you mostly probably don't have to like deal with it yourself. Most time we'll use libraries like we saw in JSON and XML to actually process this information, okay? But basically, recursion is functions that call themselves. So you can imagine like, you know, I'm trying to think of, we'll see some examples. Basically, when your function calls within itself, within itself, within itself, within itself. So this allows you to recursion. It's basically alternative to looping. This usually was considered like recursion was kind of like one of the go-to parts of early computing before, not before looping, but it was another way to do looping that made more sense. It's a little more advanced. It takes a little more thinking than just doing a loop. But the way you kind of pay for it is that it's good for unknown structures. If you don't know how the structure is going to look like, you can use recursion to recall itself. If you know it looks similar to what you had before, you can basically keep doing this function over and over again. So here's a couple examples. So I think this, I can't remember if this actually comes from the curriculum or not, or if I developed this, but just know, for example, there's a few examples like sum and max. So for example, with a sum for a for loop, if we had a list of numbers for a sum, you can imagine, for example, this is just a list from 1 to 1,000. We can define a function here. We'll call it sum loop. Basically, we'll take in a list. We'll say we start with a total of 0, right? And then for each element in that list, we will basically take that total and add up each element, right? So you do 1 plus 0, 1, 1 plus 2, 3, right? So you basically keep adding up and basically keep tracking of this total. And then once you're done with this whole for loop, basically iterating through the whole list, okay, we return that whole total, right? Pretty simple. So if I go ahead and run this guy, I have my function sum loop, and you can see here, okay, this is my list here, and I'm just going to go ahead and add it all up. And you can see here, it's 499, just a little under 500,000, okay? So you basically added up each individual one. For example, if I just put off by 99, it will be off by 1,000, right? So you can see here, added off extra 1,000. Okay, cool. So make sure I have that right there. So that's for loop. You know how to do that, hopefully. This doesn't seem like completely foreign to you, right? We're just iterating, basically grabbing each element out of the list and adding it to our total, okay? Recursion adds a little kind of funkiness to it. So usually we have things like, I'm not gonna go into full, like I'm gonna make this really clear. There's a lot more I can talk about recursion and like computer science stuff. I'm not gonna go really into that full detail because to be quite honest, it's not something that you're gonna have to like really dig deep in as a data scientist, but you should be aware of like how these things work, okay? So the first thing though is basically we get a list, And recursion acts a little differently. So for example, if my list is empty, basically there's no elements in this list, so you see the length of my list is 0, then what should the sum be? It should be 0, right? There's nothing in the list, right? So that kind of makes sense. Like, okay, we should go ahead and return 0. So if I add an empty list, it should give me 0. No, this is actually kind of nice is because if I give an empty list here, like for example, if I just gave, let me just show you real quickly. If I gave an empty list right here, you'll see it gives me 0, which kind of makes sense, right? Because that's our total right here. That's kind of what we want. So we want the same thing to happen right here. We want to give these two functions, give me the same answer, right? What the sum is. So if the length of the list is 0, return 0. Okay. Otherwise, if there are things in the list, we actually want to say, okay, get the first element in the list, and then just add up the rest of the list in here. Okay. So this is kind of like what you're saying is that when you do this part, like for example, I'm just going to quickly write this out. So like if you imagine if I have like the numbers, you know, like let's say 1, 2, 3, right? Essentially it's like, okay, let's grab this first one right here, cross it out and say, okay, the sum is 1 plus whatever is in the rest of this list, right? That's essentially what we're writing here. It's like, okay, grab the first one, okay, and it's 1 plus whatever is the whole sum of this. If someone told me the sum is 5, cool, I just put 5 here, right? But instead of just actually using a function as a sum, basically, okay, let's do the next part. Well, this is basically, this guy comes from, grab the next one, plus whatever is inside the rest of the list, okay? And then this one right here, well, that's grabbing the first one, plus whatever is in the rest of the list. What's this one? What is this? Based on our definition, what's the sum of this list that's empty? 0, right? So that basically comes through here, say, oh, okay, this is 0. So then we say, okay, this is 0, cross out, this is 0. Okay, 0 plus 3 is 3. Cool, so we cross this out, get 3. 3 plus 2, oh, that's 5. That means this whole thing is 5. 5 plus 1, oh, that's 6. So the whole thing is the sum of 6. That's essentially what our recursion function is doing. So that's kind of like what me visually going through it. I'm going to walk you through code. And if your brain hurts after this, you're not alone. It's not, I think it's not an easy thing to grab through. So we'll kind of go through a little bit. So imagine you have an element, a list of just one element in it, right? So let's say, okay, we go through this, is our list empty? It's not empty, so we're going to do this card. So we're just going to return whatever my first element in the list is. Let's say the element is just the number 1, right? So it's like, okay, we have the number 1. Okay, we're all set, ready to go. And then say, okay, plus the sum of whatever's the rest of my list, right? Well, this right here, the rest of my list, if there's only one element in there, what is this list? It's empty, right? There's nothing in there. So basically this will say, okay, doing 1 plus whatever the sum of the rest of my list is, and then we'll basically say, okay, well, that's using this function. So we go back into this function. Is my list empty? Oh yeah, my list is empty. So say, okay, that means my list is empty, return 0. So this right here will be replaced with a 0. And then we do 1 plus 0, and return it, and okay, cool. And then you have your number 1, right? If there are 2 elements in that list, it goes a little bit deeper. So let's say it's 1 and then 2, okay? So I'm gonna see how I can do this. Well, okay, I'll try to do it verbally. We'll see how well this works. So we have our list of 1 and 2. We put it through his sum recursion. We put the number, he says, okay, is our list empty? No, it's still got stuff in it, right? So we go here. So okay, grab the first element, which the first element in this case, I'll write it down here, so that way it's a little easier to see. My great handwriting too. Okay, so you can see 1, 2. I grab my first element, which is just the number 1, right? So it's like, okay, cool. First number is number 1. Okay, then you say the sum of what's the rest of my list. Well, the rest of my list is just, I'll just put sum. Well, the rest of my list is 2, right? So we don't know what that is, so we have to basically use this function. We go back into this function and say, all right, we have a list now of 2. Okay, and it says, all right, is your list empty? No, it's not empty. So if we go to this part, okay, grab the first element of that list. So you can imagine, grab the first element of the list, which is 2, plus the sum of an empty list, right? Whatever's the rest of the list, okay? But then we say, okay, sum of the rest of the list, which is empty. We go back into our function and say, okay, is the list empty? Oh yeah, it's empty. So we go ahead and return 0. So this guy will be 0, okay? So this will return 0. So basically we get, okay, 2 plus 0, that's 2. That gets pushed back up. This is 2, so 1 plus 2 is 3, and so our total return is 3. And we can basically do this with however many elements we have in that list. Okay, so it's kind of weird. Like, I think for most people, you wouldn't do it this way. I think most people would intuitively add up a real list like this, like in their head. Like if I told you add up these numbers, you probably would say, okay, the number is 1 plus this part or this part. Basically, you would keep doing the total. I think most people wouldn't say, okay, let me do the sum of the list in this way. It's not really intuitive. I think most people don't think recursively. But it does in fact work. And just to show you guys that it does in fact work, because remember, let's actually do this. So you can see here, that's our number. You can see our sum of recursion is, oh, I got worried there. I was like, it's not the same number. All right, so it should be 1,000, right? So see here, we have the same number. So note, however, if you notice on I have a little extension here. It actually executed in 2 milliseconds, executed in 2 milliseconds, executed in 4 milliseconds to add it up, which makes sense. It takes some time to go through the list. You'll notice that recursion tends to be a little slower. Not every time, but sometimes can be a lot slower. In this case, it's 7 milliseconds, which is not a huge difference, but we'll see this actually start adding up. For example, if I do, let's see if I do 3,000. I don't know if I'll do 3,000. That's too big. So you can see it's starting to hang up right here. And it might actually say, oh, too many recursive. You see, too much recursion, basically. But if I do 3,000 here, you can see basically nothing really changed. So you can see recursion sometimes can have difficulty depending on how it's designed, on how quickly it can iterate through it. If you're really good at doing recursive functions, you can figure out better ways to do this. But in some programming languages are better, but we're not gonna worry about that. So another example, just really quickly showing you, is max. And I'm not gonna walk through the whole thing again, but the idea here for a for loop, how would you find out the maximum value? Well, basically, I think most people would do this. You look at the first value and you say, okay, this value, let's say it's the number like 5. You're like, okay, cool, 5. 5 is my new biggest value. Look at the next value. It's 5. It's like the number 4. Is 4 bigger than 5? No, so keep the number 5. And then you move on to the next one. The number is like 6. Oh, 6 bigger than 5. That's my new maximum value. And keep that value. That's essentially what this for loop's doing, right? It says, all right, give me the very first element in the list is my maximum value. Okay, my potential, basically say, okay, I'm going to iterate through it. And if my current max is less than the potential max, basically the next element in the list, I'll make that my new maximum value. Okay, and they basically go through the whole list, going all the way through until basically I get to the very end, and I'll have the biggest value in there and return that. Okay, so we can see here, for example, this will give you 4,099, right? So recursive is a really fun one. So recursion one is that basically we check first, is the length of my list actually 0? How big is my length of the list? So notice that if I actually do it this way, this will give an error. Can't do this, right? It doesn't know what the maximum is, which kind of makes sense. There's not really a maximum in here, but in this case, in a recursion, we'll actually give it a default value of negative infinity. So we'll actually see this in a second. And I just want to show you guys ahead of time what this will look like. This will actually give a negative infinity, which kind of makes sense. An empty list has no maximum. Depending how you want to translate this, this might not actually be what you want. But for this recursion function, that's how we're going to treat it. So we have our negative infinity value. Basically, if our list is empty, then we already have the maximum value. Okay. Otherwise, we basically look at the next element in the list, and if the next element in the list is bigger than our current maximum, then we'll set that to our current maximum. And then what we'll do, we'll say, okay, my best maximum right now is this guy, and then look at the rest of the list. And basically, we'll keep iterating over and over again. So you can see here, I think this is not going to work because there's too many values. Yeah, I don't know. I think I was trying this as a demonstration. So if I do 1,000, you can see 999 is my biggest value. And you can see here my max recursion here is 999. So basically it does the same thing. Note that, however, in this case, it went a little bit faster. I actually don't know if that's just a fluke. This could actually be just something because of the way it works. So 4 milliseconds in this case, 3 milliseconds. And this actually might make sense because you're not having to compare every single value. You have to compare if it's the next one over. So note that this basically, there's sometimes it goes faster, but you'll notice that once I get high enough, for example, let's try 2,000. I don't know if 2,000 is going to be too big. Okay, you can see 6 milliseconds, but for 2,000 here, it's still 4 milliseconds. So you can see here is that on certain cases it's faster, certain cases slower. So just be aware of those kind of things. But they effectively do the same thing. Okay. Any questions on recursion of what's going on here? The main thing I would say take away is know that it's calling itself. This max recursion is literally just calling itself over and over again. And basically, it's kind of like a divide and conquer. It takes just one element at a time and divide it out, which part of the reason why it's slower. But any general questions at all?
I have two. Sorry.
Okay, okay.
One, if the number it's too high, then the function just doesn't work. That's what happened there.
It turns out the reason why it stops is because Python's not designed to have that much recursion. There's certain programming languages that are actually designed to have an arbitrary number of recursion, but basically Python's not designed to that. That's why it fails.
Okay. And the other question is there a risk of getting an infinite loop like we can get with for loops sometimes if you don't, do the proper stuff to not do that? Or no?
Yeah, I guess there's certain situations I could see it getting, like just like in for loops, you can have certain situations where maybe not such a for loop, but more like for like while loops, right? Which are kind of like for loops. You could have an infinite loop. Recursion could possibly do that if, for example, let's say if I have a recursion, a function that says in the function you have a number, let's say get a number and return like some other number, whatever that is. And let's say, return recursion, like if the number is 1, return recursion of 0. And then I have in that function, or otherwise, if the recursion number, or if the number is 0, return recursion of 1. It would keep going back and forth, back and forth, back and forth, back and forth. That would kind of be the equivalent of like an infinite loop. So you have to design it, obviously, to be, like you have to be careful with your design, basically. But for the most part, I think recursion tends to be much more divide and conquered. So you have what you call a stopping. Basically, this is my stopping part, and you have a stopping part. And when you have a stopping part, it's just less likely to have a recursive going on forever. It can go so deep that it takes forever, but generally you don't see that too often, but you could technically have it. Cool, good questions. All right, anything else? Cool. And then kind of going off of what Giovanna had said is that when we do a recursion and it gives that error, one of the reasons why is because recursion, you have to essentially you have to remember all the parts of it. And if you can't remember all those parts, which is what this programming language says, there's too much to remember, it kind of fails. So you kind of pay for some of that ability to remember stuff with divide and conquer. So there's some trade-offs of why recursion, this is more computer science stuff, but why recursion is can be more useful or whatnot. Okay, cool. So this is basically generally, like I kind of said this already, like why recursion is actually powerful. Like why even bother it if you can tell it's not like always the best kind of going through. It's really good at handling general structures. Basically, you sacrifice a lot of the disadvantages or advantages a for loop has by saying, well, I don't know what the general structure is. So here you can see completely legitimate Python code. Basically, it's a list with numbers in list within it. And then also we have list within list within list, which is a whole lot of fun, right? So you can see here that basically this is not something we could plan. Like, I mean, we could plan this specific case, but like I can do this, for example, and I can say, okay, let me try to do a for loop. Let me just brute force say, all right, for x in L, just print out x. And I want to find out what the sum is, right? So we do the same thing, total equals 0. And for each element in here, we basically say print x, we'll just see what the element is, and then we'll add up that part, the total to x. So you can see the first element here would be 1, but the next element would be 2, 3, 4, 5, 2, 3, 4. And we're going to add that total. So whatever 1 plus equals 2, 3, 4, which you will probably know won't work. And you can see here, when it reaches this part, it goes, doesn't work, right? So we could do like another thing in here. It's like, well, if it is a list, for example, I could do like another if statement. But then I guess I could quickly code this out. But like, for example, if I did like if, let's see here, type L, or type X, oops, my keyboard's off center, there we go, equals a list, okay? If that's true, then we'll go ahead and say, okay, total plus equals, like we'd have to do another for loop, right? So say, okay, like for y in x, what to do? Total plus equals y, right? Otherwise, just go ahead and get the number. So you can see that's, okay, that's kind of complicated, right? But now we can actually get into this part. Oh, there we go. So you can see the same thing, unsupported part, total plus equals y. So you'd have to make sure like you get the exact part in here. I don't know why total ended up being that list. But anyway, basically, you'd have to start debugging this part. And that would only be for just one extra list within here. If I had a list within a list, that would make it even more confusing, right? So you can see that this could actually get really, really deep into, oh, that's because I have to get this part. No, wait, no. Sorry, I'm gonna ignore this part. Don't worry about this. This is me trying to code on the fly. But basically you have to get like this complicated part. So you can see like this would have to be like an if statement with an if statement and do some other funky stuff. It'd be a lot of work. But with recursion, we can actually just write one function, which it looks kind of complicated at first, but what's nice is that this will actually work for any general function that's formulated like this. Basically, it's like if it's not, if it's empty, right? Return 0. This is from the learn directly. Basically say if it's empty, that's what this not part is, return 0. So if the list is empty, return 0. Otherwise, if it's a type list, right? Basically, the next element is in there, return the sum of this guy, which is the first element, plus the sum of the rest of the list, right? And then otherwise, we just do the first element if it's not a list, and just add it up to here. And what's nice is that, I won't go into the whole thing because the curriculum shows it, but you can see here this function here, and we actually get my sum. So basically, you can see here, it goes out from out here, and says the very first element is 1, okay? And then after that, basically, okay, let me get the next element, which is 2, 3, 4. So it drops into this. It basically tries to find the sum of this 2, 3, 4, okay? It basically pops off each part until it's this bottom list right here, which basically says, okay, this right here, this whole list ends up being 2 plus 3 plus 4, and then goes on to the next element, 5, 6, 7, and basically it would add up this in this total at the very end until we get to 45. So what's nice though is that you can see here that this is kind of a general function, but imagine now if I had this, for example, in my list right here, if I was to put like another list within a list, which is just awful, right? You can see how many like elements deep that would go, right? So now if I go ahead and do this, it still works though. You can see I can still basically do the same thing. So this is nice because we can now, I don't have to know what the general structure of the original list is, or list within list. I can basically just recursively apply this function over and over and over again. Versus in a for loop, I would have to consider every single possible case. And even then, if someone adds one extra different element in there, now all of a sudden I have to consider that case. So this is what makes recursive function really useful. Okay. Any questions on like why, like again, like why would you use recursion? And not so much about how this function works maybe, because I know the Learn curriculum talks about this. No, okay. Just know for these conditions, basically it's just saying, is it an empty list? Is it, if it's an empty list, just return 0. If it is a list, basically it's considering, just get the first element based on, or that first element in there as my sum, it'll pass it back into my sum. And then otherwise it just grabs the number. If the first element is an actual number, then it just does this. Okay, cool. And there's a quick discussion about breadth versus depth. I'm not going to go into full detail about this. Basically, just know you can either go really deep into it. Basically, like how this works is basically once you hit, like, for example, this guy, which is a list, you go attack that one part. You go deep into it first, and then say, okay, I hit this part, and then pop back out, and then continue on. Or you can do breadth versus first, where essentially you just do all the first letters. So you could just find all the numbers first, okay? And then go into all the first list areas, go into this part, the first numbers. Basically, you kind of do a layer by layer for breadth. Depth is like you go all the way into it and pop out. So you can see here, basically, this depth part goes smaller, 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 and pops out bigger, 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 smaller, smaller, like that. I think there's an example here for a breadth example. So this is a depth one above. This is a breadth, and you can see the breadth here basically has less layers on here. Okay, so basically you just continuously are just making it smaller and smaller versus here we go really deep or really wide, deep, 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 and then pop back out to outside again, deep, 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 and go further. This one basically is attacking at that same level each time. Okay, to be honest, this is not something you have to worry about too much. I wouldn't stress out too much about like like recursion, what's going on, but I would definitely read it through the curriculum. It kind of gives some more examples and a little bit more cases. And there's also a little thing right here from brilliant.org that kind of explains a depth first versus breadth first versus depth first, or deep first, depth first. There's some advantages of why you want to do one or the other. But basically, just know they're both essentially looking at recursion. Okay. All right, so that kind of ends all I need to really talk about recursion. Any general questions about it? Okay, so hopefully now you see kind of why it's useful. Basically, it's definitely more complicated. I will say that, is that it's definitely more complicated than doing a for loop and stuff. But the way you kind of pay for it, the reason why you'd want to use it, the advantage is that you now have something that can do a general structure where you don't have to worry about, exactly how, assuming that you programmed it correctly. So this essentially is what we are doing with the JSON and XML parsers. Basically, the Python code is doing it recursively, going through, figuring out what to do. Obviously, it's more optimized than what I could write right now, but essentially that's what it's doing. Cool. All right. So any last questions? No? All right, so I'm going to stop recording.